Okay, good morning everyone. Shine is here. Let's start the second demonstration this week. So today we are going to go through some different structures with different supports. And here the main purpose is to study the forces on the system which are needed to keep that in equilibrium. So Um, these are mostly two-dimensional cases, and the prerequisite for doing that is hi, to know the different support types and how do they resist to the morning. I mean, so in this demonstration, we keep doing the equilibrium of the structures under different two-dimensional, three-dimensional loading. And like I said, the key prerequisite for doing that is you need to know the different types of the supports, because in studying the structure and making the free body diagram, the first thing we do is we either separate the entire structure or a part of the structure from the universe, and then we study that within the frame of a free body diagram. So the the need for that is you need to know how different supports offer resistance toward the movement. For example, here I start with fundamental problem 4-3. This is a truss structure. A truss structure is a very common type of a structure. Perhaps you have seen that in the construction sites when they are making tall buildings for all construction material to be just carried around the building. They would erect a crane which is mostly made of the truss structure. Have you seen them? So they have a pillar vertical and then with a gantry which lets this is to move horizontally, and then it has cables, motors to lift heavy constructional material. So these structures are very important category of the um, structures we study very soon, maybe in a matter of week, and also just to emphasize that your practical is mostly oriented around the truss structure. So I have tried to help you with understanding the unit, not simply by doing the problem, but by doing the projects. I have added 2 projects into this unit, and these projects, I mean, practicals, you have practice 1, 2, 3. Each of them are worth of 10%. So that is a big help to everyone. The first one, second one, there are both of them related to the truss structures. All right. So once you understand them first, it helps you to get a better understanding of the applications. And with the assessment, I think this is a fairer assessment to give you some time to work, understand, and apply your knowledge. Anyway, so the advantage of a truss structure is, imagine if something of the size of 10 meter by something like 5 meter. If you were going to construct this out of the solid wood, what was the weight of the structure? If you wanted to construct this made of the solid steel, so it would have taken a Hercules to take and move this around, right? So this is easily disassemblable. So when they want to transfer the structure from one point to another point, all they have to do is to separate the joints, and that becomes a packed, very compact thing to transfer. And they would easily erect that, and that truss structure is a very efficient way of using material, right? It provides a significant uh, structural integrity. Also, you're using material in a minimum sense. It can take huge loads. So all you have to do is to understand how this creature can be studied. So that here we don't go into the detail of what forces develop inside the structure. We simply want you to understand what forces develop at the supports. But later on, when we get into the truss structure, the purpose is you want to know, if you apply 10 kilonewton over there, what forces develop in each individual member. Why do you want to do that? Because you want to know what is the critical member in that structure. You only have to be mindful of the critical. Whatever is not critical, it still can take some load. But you keep an eye on what is critical. That's a bottleneck. So that is the main objective of studying the truss structure. And we offer different techniques to study that. But for now, even as a prerequisite to finding individual forces, you need to find first, in most of the cases, you need to find the reaction forces in the support. So this problem, please listen carefully. If you didn't understand, just stop me 100 times. I'm happy to say that in different words, making sure everyone understands. All right? All right. So here, I want to find out the reactions at A and B. That's what we do. That's the purpose of free body diagram. So how do I do it? Is, well, this little toolbar is taking my access to the tools. Yep. All right. So, all right, it's better now, hopefully. Not yet. Okay, so what I do is I'm making some inside outside division. So that is the part which I'm going to release. How many releasing points are? How many support points? A and B. All right, so let me release A and B. I just want to do this in a very graphical way. Everyone sees what we are doing. So I'm going to take this away from here, from here. So that shows you the scissor. The scissor, I'm making a closed envelope. So that closed envelope, I managed to separate that from the universe. Now let me bring and put it here in my laboratory. So my laboratory is called free body diagram. So making that a bit smaller, you can see it easier. Okay, so B, what type of support that is? Am I releasing that from B or am I releasing that from the roller? I have two options. I can release it with the roller or I can release it without the roller. If I release it without the roller, that would be point B, that would develop two reaction forces. And then that's a problem. Why? Because at A, this is a pin support. I have two reactions over here, two reactions over here. Difficult to solve, isn't it? Still, I'm not saying it's not solvable. I mean, you can see the entire structure as a three-force member. If you see that as a three-force member, then the three forces should collide at one single point. So that gives you an idea about the direction of the forces, and that removes the need for, um, this is not indeterminate. You can still find the forces, but an easier approach is instead of releasing at B, releasing it at roller. So let me draw the rollers for you. Just try my best. So I kept that roller head with it. So in this case, I only have to worry about the resistance of the roller against the ground. And that is, what is the direction of that roller to the ground? It's normal to the interface, isn't it? If that roller was going to slide, what was the direction of movement? You have to draw the resistance normal to that movement direction. So that is what you do. This is called contact. Contact is whether you have roller against the surface, you have the cylindrical faces pushing against each other. This is called contact. Whenever there is a contact, how do you find the direction of reaction? First, you have to visualize if that was going to move. What was the path of movement? Here, the path of movement, if that was going to happen, the path of movement was like that, right? I call this a sliding direction. So normal to that sliding direction, that's the reaction force. So here, let me expose the reaction force here. The reaction force was there before releasing, but that's hidden. I didn't need to worry about that. When I cut it, it becomes live. It has to be exposed. And now, if I release A, how many forces would be exposed over there? That's a pin support. Two, yeah, okay, two forces there. And we don't know the direction, that's okay. We assume that they are in the positive direction. Later on, we might be proven wrong. All right, I call this, labeling is important. I call this AX and call this one AY. And this one, let's call this BY. All right, that free body diagram is my laboratory. In the exam, when you are providing your handwritten solution, just make sure you include your free body diagram. That has a big mark. Even if you get all the solutions wrong, just the free body diagram by itself, that has a significant amount of the mark. Put it there, show me that you, help me understand where did you get it wrong, and then hopefully you get what you deserve for that solution. All right. So here I have three unknowns, three conditions. So the problem is solvable, right? The question is, we want to be lazy, we want to be smart. We want to do the minimum step of calculation to get the answer we want. So from the three conditions I have, let me remind you the conditions. The first one is the net forces horizontally is equal to 0, net forces vertically equal to 0, and net rotation with respect to any point is 0. All right, which equation here gives me a straightforward answer? Which one is the best to start with? What if I try fx? What do I get if I apply fx? The only horizontal force I have is ax. So equation number 1, 2, 3. If I apply with 1, the obvious answer is ax is equal to 0. And in many problems, you can do that even without writing the equilibrium. Just by experience, you see there are all forces are vertical, therefore there is no horizontal force there. Equation number 2 is not convenient because I know the sum of A y A B should be 10 kilonewton, but I know the contribution. I don't know which one takes and how much. So maybe it's better to continue with equation number 3. Equation number 3, what is the smartest point of rotation? One bullet to kill two bad guys. Yeah, the bad guys are unknowns. A is the best rotation point, right? That would kill two unknowns. So if I choose that center of rotation with respect to the A, that is very straightforward. And all I have to do is I need to find the shortest distance between this force and the center of rotation, which is A. So in another word, I have to draw a normal from here to there. Can you tell me how much that normal is? So I'm trying to calculate the normal. That is 2 plus 2 plus 6 cos 45. Everyone can see that? Okay, so the radius is 6 plus 6 cos 45. That's all you need to know, and everything else is simple. So from this point, I can write By with respect to the A. Does it rotate positive or negative? Positive, yes, that's positive By multiplied by this arm of rotation. Okay, let's not be 6 plus 6 cos 45. And then 10 kilonewton. That makes a negative rotation, doesn't it? So that's minus 10 kilonewton. And I remember by doing that, the unit of the forces in my equation are kilonewton. If I keep everything to kilonewton meter, I don't need to change the unit. And the arm of rotation for that is in a similar fashion, that is 2 plus 6 cos 45, correct? Equal to 0. And that equation has only one unknown. So here I can work out By. And now that I have By, all I have to do is Ay plus By is equal to 10 kilonewton. So I take away By from 10 kilonewton. 5. Yes, yes, thank you for that. I almost missed it. Thank you, Nguyen. So 5 kilonewton is an easy one. Why this is an easy one? Because to find the radius of rotation of 5 kilonewton, what is the radius of rotation of 5 kilonewton? 4. Excellent. Right? So that doesn't need trigonometry. That's a straight. You know the shortest distance between A and 5 kilonewton is 4. All right. Is this a positive or negative, Nguyen? Negative. Yes, correct. Thank you for that. So I add minus 5 times 4 equal to 0. And that is all you need to calculate By. I leave the calculation to you. Let's spend time with explaining the problem rather than. Sorry? No, that's simply 4. The shortest distance, you draw normal from A to the line of action. Let me show you that. So this is line of action for 5 kilonewton. That's line of action. So you draw a normal from here to there. The distance is 4. Yeah. All right. So here you find By, and once you have By, then By take away from 10, take away from 5 cos 45, that is equal to Ay. All right. So I write you the expression for the second equation. The second equation, I assume that you have calculated By, so this is not unknown anymore. So if you apply equation number 2, that would tell me Ay plus By minus 10 minus 4 cos 45, that is equal to 0. So By you already know. The only unknown in this equation is Ay, and then you find the reaction of A. Sorry? Cos 45. How did I get cos 45? So that I need to resolve that into two components, right? So two angles which are mutually perpendicular are equal. So this angle, the side is perpendicular to this one, and that side is perpendicular to this one. So that angle is 45. Yes? So that's in a geometry. If two angles have their legs mutually perpendicular, they're equal. Uh, well, we are talking about the vertical one. If that is 45, that would be cos. Cos would project it on vertical line. All right, let's go back to another one, 4-4. Any question with that? Yeah, yeah. Let me zoom out. -4, that is this force you mentioned, 4 kilonewton. That's 5. Yeah, that's 5. That should not 4. This is 5 cos 45. That is this force here. Yeah, that force, if you project it vertically, that would be in a negative y direction. Questions? No question. Let's move on. 4-4. Okay. Um, this one is relatively different with what we have done before. And the reason is it has a new type of support. The support at A, do you know the name of that? Cantilever or fix? And how a cantilever resists to all the forces? It resists against the horizontal translation, vertical translation, and resists against the rotation. So there, it develops 3 unknowns. If I want to release that from the universe, I have to cut it from A. So that is how do I cut it from here. Now, what I have requires exposure of the forces, and the internal forces at now has to be exposed. What do I need to include here at A? Need to include three forces: reaction against vertical movement, horizontal movement, and also rotation. I don't know whether the rotation direction would be positive, negative. Let's just assume that this is in this direction. I call this MA, this one AY, and this one AX. Labeling is a very important part of the free body diagram. So that is my free body diagram. This is my laboratory. In this laboratory, I'm studying the forces. I'm calculating the forces. So that is not very difficult. I mean, given that I have three equations, net forces horizontally equal to 0, that's equation number 1, condition number 1. Condition number 2 is the structure doesn't move vertical. Condition number 3, that is the structure does not rotate. Net rotation equal to 0. All right, tell me which equation is reasonable to start with. Which one? Fx. Well, fx, if I apply fx, yes, you are right. Fx would give me f of x. All right, thank you for that. So if I start with equation number 1, that is plus 400 cos 30 plus ax is equal to 0. So ax is minus 400 cos 30, which is 30 cos multiplied by 400, 346. And the unit is Newton, right? Because everything is in Newton. All right, what is the next equation? Yeah, I think we can do the y, can't we? Right? So if I do the second equation, that is cos, sorry, 400 sine 30 in a negative direction. That is minus 400 sine 30. Sorry? AX is negative. Yes, yes, that's negative. Thank you for that, Marianne. Thank you. So that is minus 400 sine 30 minus 200, 200, 200. That is minus 600, right? Plus AY is equal to 0. So that is minus 200, minus 200, minus 600, minus 800. AY becomes 800 Newton. If that equation only asks you to find the bending moment at A, what was the best equation to start, to apply? If you are not interested in AX, AY, could you just jump into equation 3 and doing it to find the bending moment? Yes or no? Yes, because by taking the center of rotation at A, you get rid of AX, and then the only unknown in the equation becomes MA. So that's how we find MA, taking rotation with respect to, I mean, now that we know AX, AY, even we can take rotation with respect to this point here. But the problem with that is, if you do it, this solution depends on your solution of the previous step. If you made a mistake, then that mistake propagates here into MY. So you want to avoid that. So let's take the rotation with respect to A. In case if I made the wrong calculation, like Nguyen mentioned, I missed the negative sign. This thing could easily happen. So that's why it's always make the solution independent if you can. And I make this one to rotate with respect to A. So that is MA. So the third equation, third condition, that is my MA minus MA, because that's clockwise, minus 20, that the arm of rotation is 3 cos 60. Cos 60 is half. So this is 1.51, this is 2.5 times 200, and then minus another 200. This one is 2 plus 1.5 is 3.5. And the last vertical one is minus 200, 4.5. And then that 400, I have to break that into two components, right? Or if I can just find the shortest distance between A and 400, that's one way of doing it. Say it again.
Minus n and minus 2 into 200 because 3 and 1, 4, 4 and half is 3.
Well, that is minus 2.5. That is 1, 1.5, 2.5. This is 2, 1.5, 3.5, and the last one is 3, 1.5, 4.5. What's the problem?
How do you calculate this one? 3 plus 2.
The third one, or?
First one.
Yeah, the first one. The first one, what is that length from here to there? That is 1.5. That's 3 times cos 60, which is 1.5. Now, still, I need to find the rotation of 400 with respect to the A. So to do that, let's break that into two components. That is 4 cos 30. Cos 30 is root 3 by 2. So 400 times 30 cos is 346.4. And then the vertical component is 200. So that 200, these 200, I can combine them and make this one 400. Sorry for being lazy. And this one, what is the arm of rotation for that? Arm of rotation is, I need to make the line of action for this force. That is my line of action. And then from here, I draw a normal to that. So this is going to be that side, which is 3 times sine 60. So 3 sine 60 is 2.6. So that is 2.6. And the rotation due to that is also negative. That is minus 200, sorry, minus 346.4. and arm of rotation is 2.6 is equal to 0. All right, that equation only has one unknown, which is ma. And just by looking at the signs, it is very clear that the sign shouldn't be clockwise, should be counterclockwise. You get a negative number for ma, so that means that the bending at a is counterclockwise, the answer. All right, questions? Is that correct? Yes? Which one? X direction? All right. X direction, um, X direction. You might be right. With the X, we didn't include the, or we did. Right. So this free body diagram, what are the X forces? The only X forces are AX and the component of 400 in the horizontal direction. So if you project 400 horizontally, that is 400 times cos 30, and that becomes 346.4. So that's the only horizontal forces. Both of them are in the positive direction. So you add AX plus 346.4 equal to 0. And by solving that, AX is minus 346.4 Newton. Correct? Ian?
No, this is minus equation.
All right. So these are all negative number, right? So the first one, yeah, this is negative, that is negative, this is negative, that's negative. So everything is negative. You take that to the right hand side, that is positive. So minus ma is equal to a positive number. Ma becomes a negative number. I mean, just to do the number. If you cannot do it in your memory, just use calculator, solve that equation. What you get for ma would be a negative number. You find the assumed direction is not correct. It should have been counterclockwise. We assume this to be clockwise. Just, yep.
This one?
All right. So that is, you miss one term. This is not sigma m. That is ma. That's how much torque develops here. This is not sigma m.
So
Yeah. That's
why in the previous but in
yes.
we don't have the
Because that has a pin. The pin is free to rotate. It doesn't resist against rotation. But here, this is like you bolted that to the ground. It cannot rotate. That's a cantilever. That's the difference between cantilever and the pin. Good
so
question.
the image just a,
Yes. When you want to release it, you need to expose the internal forces. For the fixed end, the internal forces are not only the horizontal vertical, also bending moment. That is in Monday class, we summarize all the reaction supports. And this reaction, it has a name. It is not called pin, it is not called roller. What do we call it? Cantilever. Let me draw that for you. The cantilever is something which is either welded to the wall, right? So you just show it like this. This one, if you try to bend it, this beam doesn't rotate. It doesn't move horizontally, it doesn't move vertically. This is like a truss. Imagine you go to the truss, suddenly the truss rotates, what happens? You just fall, right? The truss should resist against the rotation.
also like when you
Yeah, this is a truss.
when you release this goes this way. So
It cannot
this,
rotate because this is being welded to this and the weld has been bolted to the ground.
so the image direction is always like this.
No, we assume that the resistance is counterclockwise. That's how you start. You start because you don't know the direction, and when you solve that expression, it gives you whether your assumption was correct or you have to reverse it.
Okay.
Yeah?
So,
Good question. Thank you for asking.
so what about the 200 force down?
200 force down. What about it?
We didn't add that in
That I integrated in another 200. That was 200. I was lazy. This is 200 here, 200 there. I combine them together, that comes 400. So 400 multiplied by the same radius. I could have split them. I merged them together because I was lazy. Yeah, just wanted to save ink and save air.
We solve the three one, and then
Yes, you find MA, the last one.
so the MA is about the so minus M minus the whole zero.
Yes, that give you MA. The magnitude of MA give you a negative magnitude, which tells you, look, the direction you assume should be reversed. All right, I think the only person who remembers a cartoon in the ABC channel is Darcy. Darcy might remember Lazy Lucy. Do you remember Lazy Lucy? That was a cartoon character. She was a lazy girl, but lazy in a good way. A smart lazy.
All the engineering.
Uh, Cartoon, yeah, cartoon, yeah, yeah. Lazy Lucy, she was a lazy girl, but a smart way. So you, as an engineer, you want to be lazy but smart. So you get a salary, just try to not overdo it. I mean, just spend what is correct, um, what is optimum. If you do extra, you might be accused of not being smart. Why didn't you do it in an easier way? Why did you go through a different way? I want to go from here to there. Why should I make my way farther? All right, let's move on. Go to number fundamental problem 6. All right, that's a very good question. And that is a best explanation for contact. If you understand this problem, perhaps you have no issues with solving the contact problems. And I tell you why. All right, the problem here is I want to make a free body diagram, and I have not only one contact, not two contacts, but three contacts. So when I release that lever from the universe, that is my envelope. Let me show you my envelope. I want to make a free body diagram by releasing that from point C, releasing it from point A, releasing it from point B, and this is my envelope. Anyone can see the envelope? All right. How many releasing points? Nguyen, how many releasing points are here? If I take my free body diagram like that, three, yes? And what are the type of the contact? What are the type of the supports? Contact, okay? With the contact, we know that there would be, if there is no friction, with the contact, there is only one reaction. And the reaction is normal to the interface. And the question is, are you able to get the right direction of the forces? Make sure you watch yesterday and what you missed from today. Thank you for that. All right, so this was a very important session for free body diagram. Please watch the recorded. That's the best favor you can do for yourself. All right, so let's release that, and I want someone to tell me how to include the direction of forces. Okay, at point C, the question is, this question I asked from um, Porty. Porty, the reaction force, should it be, which one is my interface? Should I make that reaction normal to this face, or should I draw it normal to the lever direction? So I know the reaction is at point C, but the question is, should I draw it normal like that or normal like vertical? Normal to the rod. Yes? Anyone in agreement with 40 hands up? Anyone disagreeing with 40 hands up? It's either you agree or disagree, right? So I'm not gonna kill you. Just tell me what you think is correct. I think 40 is correct, but the justification of that is important. So here you don't know whether to put the force normal to the ground or normal to the rod. How on earth Porty realized that this should be normal to the rod? I think his justification was, if the rod is going to slide, what is the direction of sliding? The direction of sliding would be like that. Normal to the path of movement, hypothetical movement, that is the direction of the force. Okay? So that is why who am I to argue with 40? All right? So you're right. Okay, with the same justification, tell me at point B, should I put the force like so or normal to the rod at point B? So point B, I don't know whether my reaction force, contact force would be vertical or normal to the rod. Which one, normal to the rod or vertical? Yes, I explained. If that lever starts to move, how does it move? I mean, the ground doesn't move. The ground stay where it is. The sharp edges of C remains where it is. It's going to move along the rod. That's the path of movement. It never moves, but if for some reason that's going to slide, the sliding would be the along the lever, which is at 30 degrees. If not, it doesn't slide horizontally, it doesn't slide vertically, because this is in contact with the rod. It should follow the periphery of the rod.
Can you point it on the board? How is it going to slide?
Yeah, let me show you. That is how this one is gonna slide. If that slides, it would be sliding either down or would be sliding up. It never slides vertical, it never slides downward. Yes? All right. With the same justification, can you tell me at point B, what is the direction of sliding? Is that horizontal sliding, vertical sliding, or sliding along the rod? No, it's not along the rod. Because this is rod moving. This is not the ground moving. Ground is always fixed. If you keep sliding the rod, point B moves horizontal. If you move lever, point C moves at 30 degrees. If you move lever, point B moves horizontal. So the reaction for that would be just vertical. Okay, last one. Last chance to apply your skills, your knowledge. Point A, if the rod slides, does it slide normal to the lever or normal to the ground? Normal to the ground. Ground is fixed, so the tip of the lever at point A can only move horizontal. If that's the direction of movement, normal to that is what? Normal to that is like so. Okay, the next step of every free body diagram is labeling. If you do labeling correct, let me just simply call this C, B, A. I could have used X and Y indices, but in that case, I mean, we can just limit it to these. All right. How many unknowns this problem has? Just the magnitude of the forces, the direction we know, right? So three unknowns, three conditions. All right. So what is the easiest condition to start with? I mean, I have three conditions here. My first condition is the structure doesn't move horizontally. That is condition number one. Condition number two, that is structure doesn't move vertical. And the third condition is structure doesn't rotate. So which condition is easier to apply to begin with? All right, I think if we take the forces in x direction, I mean that's my x, this is my y direction. If I take the forces in x, the only forces in x are 250 component and c component, right? So that is solvable. That would be minus 200. That's equation number one. Equation number one, condition number one. That is 250 Newton projected horizontally, which is projected horizontally. If this is 30 degrees, that is going to be 60 degrees. So that 250 projected horizontally becomes cos 60. And then how do I project C horizontal? So C horizontal is, what is that angle? Can you read? This is 30 degrees. See, this angle is 30 degrees. This angle is 30 degrees. So if this is 30 degrees and I want to project this one, that is 6C. Again, this is plus C cos 60 is equal to 0. Yeah, that is 30 degrees. Let me plot that triangle again. So with this triangle, that is a 30 degrees. This is a 90, that's going to be 60 degrees. So 60 degree projected horizontally, that is C cos 60. What about this one? This one, I want to project that in this direction. So this is 30, that is 60. 60, this force cos 60. All right, so here I find out C to be equal to 250 Newton. Now, to find out A, um, I mean, I can use either of the equation. Either I can take the rotation with respect to the B equal to 0, or I can take some of the vertical forces equal to 0. Some of the vertical forces equal to 0, that is 250 projected vertically is minus 250, that's equation number, condition number 2. That is 250 vertical projection is sine 60. and then C projected vertical, that is plus 250. Sorry, this one is a negative, minus 250 sine 60 plus B minus A is equal to 0. So that has two unknowns we cannot solve. So just let's keep it, postpone use of that equation to the last stage. Now I apply the third one by taking rotation with respect to point B. With respect to the point B, yes, what is the distance of, yeah, point B, I resolve that force into two components. One is perpendicular to the rod, the other one is tangent to the rod. So perpendicular and tangent to the rod. The tangent one is passing through B, doesn't make any rotation, only the projected one does the rotation. And that makes a positive rotation. And the arm of rotation is 0.4 plus 0.2, 0.6. C. C is normal to the rod, so the arm of rotation is 0.2. We have the magnitude. That makes a negative rotation. B doesn't make any rotation. A makes a negative rotation, but the arm of rotation is 0.15 multiplied by cos of this angle. So what is this angle? So that is 30, 90 is 120, 120 take away from 180, that's 60. So this is 60. So that arm of rotation between here and there, that is cos 60, which is half of 0.1. So I leave the calculation to you. Then the main thing with that problem was to get the forces direction correct, and hopefully everyone is there. Page, yep,
Can you go back?
yep. I'm recording it. Don't worry. You can watch this recording.
That one, which one did you have?
I took the point of rotation B. B. So plenty of problems left to be completed. We go to page 197 to 200. Okay, you want the easy one, you want the difficult or medium, what do you want? Let's do 4. 4 is a relatively medium to difficult. So this one is a truss as a bridge. This is like a bridge. You put a truss structure between two supports in a gap, and that is truss structure as a bridge. Okay, I want to find the reactions. If I release pins at A and B, that's going to be difficult. Why? Because pins make two reactions. You will get two reactions at A, two reactions at B, four reactions. The problem is not solvable. So what's the remedy? The remedy is we don't release it at B. We release it at the tip of the roller. Okay. If I release it at the tip of the roller, um, then my structure will be something like that. And let's just first start with the external forces. The external forces, 5 kilonewton is here, 6 kilonewton is here, 8 kilonewton is here. And now all I have to do is to include expose the internal forces. So that is one, I assume this one, this, and this one as, the tricky one is the contact at B. Contact at B, the direction of sliding is vertical, normal to the, sorry, horizontal, vertical to the horizontal is that one. So the key is, well, first I put the numbers 5, 6, 8, and then everything else you label them, that is AX. I didn't know whether that is X or left or right, just assume AY the same, BY the same. We just assume these are the positive direction. How many conditions we have? 3 conditions. How many unknowns? 1, 2, 3. The problem is solvable. Condition number 1, the structure doesn't move horizontal. Condition number 2, the structure doesn't move vertical. Condition number 3, the structure doesn't rotate. All right, which rotation point, if I want to start with the rotation equation, what point is the best rotation point? To kill 2 unknowns. A. A would kill 2 unknowns. So let's take this one with respect to the A, that I start with equation number 3. Rotation with respect to the A. All right. 5 kilonewton with respect to the A. Does it rotate positive or negative? Negative, clockwise. So that is -5. And what is the arm of rotation? Shock. What is the arm of rotation? 2. Next force is 6. 6 with respect to the A. Does it rotate positive or negative? Negative. -6. And what's the arm of rotation? 2. And the next force is 8. 8. Does it rotate positive or negative? Negative. And the arm of rotation? 4. And with B, does it rotate positive or negative? Positive. By. And arm of rotation? 6. Right? Equal to 0. So this can easily be solved. That is -10, -12, -24 is equal to -6 by. So that is 36, 46. By is 46 divided by 6. 7.67. And the unit is kilonewton. Okay? All right. So now the next equation is the second one. The second one, the only unknown is AY. And then you apply the first equation that give you AX. And then just by looking at it, I know that AX is wrong. AX should be pointing toward the left, not pointing toward the right. Because the only horizontal force I have is 5 kilonewton toward the right. AX should oppose that to cancel that. Okay, I leave the detailed solution to you. Otherwise, we can complete the today's. Page 212. All right, so these are 3-dimensional problems. And with the 3-dimensional, we apply the same conditions, but could be A scalar condition could be vector conditions. Let's do one of them. Okay, here you just want to do the free body diagram. That's easy. Free body diagram for example, this one. Let's do the free body diagram for this one. Okay, that is preliminary problem 4-2B.
Sorry. Yeah, this question, I don't really know. 9 should be it.
I might made a mistake. What did you get?
9.
9. Yeah, you're right. I think that should be 9. 9 kilonewton. Okay, so we go to the preliminary problem 4-2B. So these kind of supports, these are journal bearing. Okay, journal bearing. And at point A, the rod is free to move vertically, is free to rotate, but it's free to rotate about z-axis, but not free to rotate about x-axis or free to rotate about y-axis. So I want you to think about what forces develop here. Well, because because only one vertical force we have, there is no reason to develop a x or sorry, the force is in the z direction. The only reaction forces at CBA are going to be z forces. So A cannot take z force, right? A cannot take any z force. What about B? B can resist against the vertical. So let me include a vertical force here. What about C? Yes, C can resist a vertical force. And then, all right, so the force between 500 and C, they are making a rotation, all right? That rotation should be cancelled by resistance, rotational resistance at C. So that is against the y-axis. So let's put about the y-axis resistance Cy, and this is Cz. And the force 500 and B, they are making a rotation about the x-axis, right? So for that reason, I make a resistance Bx. So that's the free body diagram. Yeah, I explained. And the only external, the weight of the structure is negligible. Weight of a structure is negligible, and the only external force is along the negative z. So that negative z, how this is being resisted at B, it won't make any resistance in the x direction or y direction. It only can develop a resistive force in the z direction. So that's why I put the red arrow BZ in the vertical. So what about A? A. put A is free to slide at the Z, so it won't develop a Z force over there. Um, C. C resists against the motion in the vertical direction, so I put a CZ over there. Now, because of these two forces, I mean, if I add all the Z forces together, yes, BZ, CZ cancel 500. So think of a uniform distribution or non-uniform distribution, either way that they would cancel. But then they also would generate some rotation in the system. So think of how 500 and CZ can make a rotation. They make a rotation about the y-axis, right? To cancel that, you put a resistive torque of CZ, CCY, and 500 and BZ, they make a rotation with respect to the x-axis. So you include a rotation about BX. So don't worry about the free body diagram in 3 dimension. That is not for the exam. It's just if you understand it, that's good. Otherwise, just everything is limited to 2D in terms of free body diagram for the exam. Just maybe we do something more applicable to the assessment. Um, Page 213. Fundamental problem 4-7. If I release that plate is being suspended by 3 cables, okay, 3 cables, and we know the cables can only take tension, and they take tension axially. So, in another word, the only way these cables can make a resistance is that one make a tension, this one is making a tension, and that one is making a tension. All right, and that's the external force. The weight is 200 kilogram. So 200 kilogram, that is applied in the center of area of the plate. That is 200 here. All right. So the weight would be 200 times the gravitational acceleration 9.8 g. That's the weight. 2 kilonewton is also applied here. And then you have A, Z, C, Z, B, Z. That's the free body diagram. You don't expect any reaction in y direction or x direction. You don't expect any bending moment because none of the support can take the rotation, can resist against the rotation. Okay, 4-8. this is a triangular plate, and point B, it seems to me that is being suspended by cable. Is that what you... Point C, roller support A, yes, roller support A. Um, Ball and socket joint D, and the tension in cable BC. Okay, BC is a cable. It can only take a tensor. If I release the plate, the cable can only take vertical force, and the external forces are vertical. Even though a ball socket resists against the translation, but is free to rotate. So no bending moment, but also it is useless if I include the X and Y component at the ball socket because all forces are vertical. So for that reason, we only include that like a roller, this one like a roller. And then if the weight of this plate was significant, you would have placed it right in the center of gravity of the plate. But in this case, no mention of the weight, so we ignore it. Any question? Let's move on. And 4-11, okay, so this is not just a free body diagram, also we have to solve. So how do we solve it? All right, to solve this problem, we just derive the equation to be solved, and you can work out the solution yourself. DB, this is short link. The short link is a two-force member. A two-force member is like a cable. The only difference is it takes both tension and compression. Because this structure is being hanging and the forces are applied downward, I mean, it's not difficult to find out that this put my member in the tension. If you visualize that application of the load, these cannot make this one under compression. So two force member, the force is axial from B to D, but the question is this going to be tension or compression? That is tension. Even if you can't visualize, just assume the positive direction. Later you can. I call this force FBD. All right, FBD. How can I write FBD? FBD times K. So we don't know the magnitude, but we know the direction. So what about this one? That's a cable. The cable is always in tension, and I call this one FCE. So I know the direction, but I don't know the magnitude. This one is also a cable. The cable can only take tension, and I call this one FCF. And with A, I neither know the XYZ component. This is a ball socket. Ball socket takes resist against the translation, doesn't resist against the rotation. So that is I mean, you can write this in this way. Three components: AZ, AX, and AY. All right. How do we write the condition of equilibrium here? We write this as a vector. So writing this as a vector means net forces equal to 0. How do I write net forces equal to 0? Net forces as a vector equal to 0. How do I write it? So I have to add all the vectors here and set them equal to 0. Starting with external forces. How do I write 6 kilonewton in a vector? Nguyen, how do I write 6 kilonewton in a vector? That is plus 6I, correct? How do I write 9 kilonewton in vector? Minus 9K. All right, so we finish with the external forces. How do I add A forces here? So that is plus AXI plus AYJ plus AZK, correct? Correct. So far, I took care of this one, external forces, and A. The next one is FBD. So how do I include FBD? That is plus FBD times K, correct? K, that's a Z direction, FBD. And how do I include FCE? That is plus FCE times K. And how do I include FCF? That is minus FCF I. So that is, we took care of net translation equal to 0. And then this equation, if I want to solve, who can tell me how many unknowns are here? 1, 2, 3, 4, 5, 6. 6 unknowns. How many equations I have? Well, that vector equation is 3 equations. Why? Because I can collect all the I components together, put that equal to 0, collect all J components and set that to 0, and collect all K components, set that to 0. So this vector equation can handle 3 unknowns. So what about the remaining? I still have 3 remaining unknowns. I need 6 equations. Only this is 3 equations. All right, so that is the net force. Then let me um, I need to find out that net force, and then I need a rotation equation. That rotation equation, I can take rotation with respect to one particular point. So let's take rotation with respect to center of coordinate system. All right. So if you do that, so that's a very long equation. I call this point O, and then I want to apply net rotation with respect to the O as a vector is equal to 0. So that is with forces at A, that is AXI plus AYJ plus AZK, that multiplied by the position vector. The position vector is OA. And OA is what? OA is 4I. 4I as a vector, cross product at another vector. And then the way you do this is by constructing a determinant and put them in the determinant finding. So that's only the first step. And the second one, FBD is passing through B, it doesn't make any rotation, plus 0. That 0 is due to the FBD. And what about FC? This is the position vector for FC, that is OC. So OC, I write this as a vector multiplied by FCE as a vector, and then FCF the same. I can take these two added together because they share the same position vector, plus FCF as a vector. And finally, I can add these two forces with the same, let's call this point, for example, CF, G, I call this point G, this point. So the position vector for that would be OG, right? So that is plus OG as a vector multiplied by 6I minus 9K. All right, so this is another vector equation. That vector equation, how many equation, a scalar equation is a vector equation? That's 3 equations. Because you collect all the I components set that equal to 0, collect all J components set that to 0, K component. So if you solve these two system of equation, you have 6 equations, 6 unknowns, and that is solvable. All right. Don't go through the solution, and just the good news is in the exam, yes, that does not, this is excluded, but just to give you how, if you understand the concept in 2D, the 3D, the concepts are the same, except most of the cases, three-dimensional cases are handled by the computers, computer-aided design, because matrices, they are made for computer. Even there are many softwares like MATLAB. MATLAB is matrix operation laboratory. It started in matrices. So vectors are matrices, and yeah, make sure you don't miss MATLAB. That has a very strong software like SolidWorks, like Mathematica, like many computer-aided design softwares. All right, so what else? Going to the last page, 14 and 17. I think we can do one problem from each. Would you be happy if we do 4-27 from here? Okay, so we are going to release the structure at point A. What type of support is A? That's a cantilever, right? That's a cantilever. It takes, it resists against the translation and rotation in 3 dimensions. So I would include a force here as AX, AY, AZ, and also I include the moment as MX, MY, and Z. And the forces are 3 external forces, 400, 500, 600, easy. So let's call this AX, AY, AZ. and call this one MAX, MAY, MAZ. That's all you have to do. Now, starting with the first vector equation, the net force is equal to 0. How this can be written in a vector? That is AXI plus AYJ plus AZK, and then 400. How do I write 400 in vector? That is minus 400I, correct? How do I write 500 in vector? That is plus 500J. And how do we write 600 in vector? That is minus 600K. So that's all you have to set equal to 0. And then how many equations does this give you? 3 equations. Because if you collect all the I components, set that equal to 0, collect all J, set that to 0, all K, set equal to 0. And then something a little bit more difficult, that is when you write net rotation equal to 0. What is that? That is, we do it one by one. I take the rotation with respect to point A. If I take it with respect to the A, we don't worry about the translations because all they vanish, they're passing through point A. So that will be only MAXI plus MAYJ plus MAZK. That is this one. And then with the 400, I mean, I can avoid doing the scalar. 400 with respect to the A. That, if you use your right hand rule, it's not difficult to see that this is minus 400J. Minus 400 times 0.75 J. Because that rotation is in a XZ plane. Normal to the XZ plane is a Y, and it's in the negative direction of the Y. So that is minus 400. The arm of rotation is 0.75. And the unit vector is J. And likewise with the 500 with respect to the A. This is in a Y Z plane, so the rotation is normal to that plane, which is in X, but that's in a negative X direction. So that's minus 500, and the shortest distance between that, because I'm doing the scalar, 0.75, 0.5, that is 1.25. And the unit vector for that is I. And finally, that of 600, that rotation is in a XZ plane, and therefore the rotation is in a J plane. So that is again in the negative J, that's minus 600. And well, that is not easy. You have to bring it in 2 steps. First, I need to bring that to here. Maybe with 600, I do it with the vector notation. So that is minus 600K pre-multiplied by the position vector. Position vector of A to this point. Let's call this G, AG. And AG is what? AG is 1.25K plus 1J minus 0.75I. That's the position vector. So this position vector pre-multiplied by 600K, that is the rotation due to 600. And once you write this equation, that's a vector equation, can be resolved into 3 scalar equations. You're collecting all I components, setting that equal to 0, one equation. collecting all j components, setting that equal to y, second equation, collecting all k, setting that equal to 0, third equation. So altogether we have 6 equations, 6 unknowns, and that is solvable. So if you want to delegate, if you want to delegate this one to computer, that's all you need to know. The minimum information you need to pass is to know there are 6 equations, 6 unknowns, and then computer does the labor for you. 6 simultaneous equations to solve that together.
Set minus 400 and 0.75 pi.
Yes, that is because of 400. 400, that is inside, with respect to the O, that is a rotation in the XZ plane. XZ plane rotation that will be projecting out is either in the I component, J component, or negative J. In this case, if you use your right hand, 400 is in the negative J. So that's minus 400. And the arm of rotation is from A to here, which is 0.75. So the last exercise we do for today, that is from, what page was it? 217. Okay, I'm doing problem 4-39. All right, so this is very much related to the week 1, week 2. So I have to release this from the cables. The cables are developing forces. I call this FBD. And this one I call this FBC. And what forces should be included? I mean, this is a socket. In the socket, you have AX, AY, AZ. And in this cable, that cable we included. So what is left is the weight of the panel. The weight of the panel is 100 kilogram times 9.8. This is almost 1,000. So here, how many equations we have? Um, 1, 2, 3, 4, 5. How many equations we have? 6 equations. Or how this can be done? Well, first you have to write the forces in vectors, and you have to write the position vectors. Then you apply net forces equal to 0. You apply net rotation equal to 0. And net rotation is what? Net rotation is um, this equation. I expand this for you. So starting with 1,000. 1,000 is minus 1000k. And what is the position vector of this one? The position vector is AG. I have to go from A to G. For that, um, the panel, what is the width of the panel? Just had this one, not readable. The width of the panel is, do we know the size of the panel? Um, all right, so that's not a problem. That's not a problem. Why? Because I can shift the force of the G. So I can pretend that this force is applied here. If that force was applied here, what was the position vector? The position vector was from A to that line, right? So a vector is free to move along its direction. So I don't have to worry about AG. I have to write that position vector, which is 1 meter I, 1 meter J. So that is J cross product by 1000. That is the rotation due to that weight. Okay, the next one is, how do I include that of FBD? I'm taking rotation with respect to the A. That would exclude AX, A by AZ. They won't make any rotation. And now both FBC and FBD, they share the same position vector, which is AB. So that is AB multiplied by FBC plus FBD. They both share the same position vector. And yeah, AB is what? This is 2J AB. Yeah, FBD. Yeah, FBD. Thank you. And you know how to write FBC, FBD, don't you? These are just, you use the BC as a position vector, find the unit vector multiplied by magnitude of this force. No. These are just very laborious. You have to do lots of calculation, but you know how. So I don't make you saying for that operation, like I said, nothing like this would be in the exam. And just, I want you to be able uh, articulating the problem, finding out how many unknowns, how many equation, and then you can delegate to computer. Computer does the dirty job for you. So like I said, 1,000 years ago, people have human slaves. Now you have computer as your slaves. The more you know about the computer, the more powerful you are. In a good way. You don't have to feel guilty. Oh, I'm using a slave. Don't worry. Yeah, silicons don't feel pain. Just the bill, electricity bill, that's painful. Apart from that, nothing is painful. All right, thanks very much for being such a patient, wonderful audience. I just talk and talk and talk, and you listen and listen, listen. And the last thing is, before I let you go, whether you have a question. All right, here I have Sahar escaping the class like always, and Natasha being present like always. Thank you, Natasha. Nguyen being present. Thank you, Nguyen. Chaisal just skipping some of the classes. Still, I'm very thankful. Daniel away. Abdullah away. Jonathan, you won't see him again. I think Jonathan got a job. I recommended him. It sounded to me that he got the job. Yeah. Ahmed Not today. Nigel, thank you for being such a good participant. Barnaby away, Flynn away. Shaw, thank you for being in the class. Darcy, thank you for being in the class. Forty, thank you for being such a persistent participant. And I think still, for some reason, I have to refresh a name for. Um, I think it's not complete yet.
So why is my picture is not showing here? How could I fix it?
Sorry,
Why my picture is not showing here? How could I fix it?
is that your picture is not there? What is your question?
Yeah, my picture is not showing
Just
here.
go to the student headquarters and tell them, look, you haven't included my photo in my registration. So they take a photo and then include it there. All right. If you don't have any question, I look forward to see you next Monday. And thank you for coming to class. All the best.
Thank you.
So there's gonna be no 3D things in our test.
Yeah. All very simple. Nothing like this one. 3D will be very simple.
Yeah, this. Oh, so there's gonna be 3D in the test. Oh no,
It's not fully excluded, but things like this one, these are not for exam.
oh, we just need to know it.
Mostly 2D. Yeah,
Yeah.
mostly 2D.
So the test is just like from the quiz, this is similar to that one.
Similar to the quiz, similar to the one which I covered for you in the class.
Or at the end of like the test, stuff like that.
Nothing like that. Yeah, nothing like that.
Yeah.
Don't worry, I'm here to teach you, not to torture you or just to give you to a tournament, something like that. Yeah.
For week two assessment, I haven't completed yet because I cannot log in to
Send me an
Pearson.
email. I will explain it for you. All right?
Thank you. The week two.
Thank you, sir. Have a good
Thank
day.
you. You